Hi, today we will discuss deflections of determinate beams and frames. But before going through the process, we need to that we need to know the methods for determining deformations, deflection diagrams, and the elastic curve and the elastic beam theory. We have several methods in determining elastic deformations. One is the double integration, as you will see later on in our derivation of the elastic beam theory. The moment area method, or the moment area theorem, the conjugate beam method, the Castigliano's first theorem, unit load and virtual work, and the partial derivative. Of course, there are other methods that we can use to determine the elastic deformations of the structure. But that would be used later on when we talk about the statically indeterminate structures. Also, of course, with the matrix structural analysis, we use a different method in determining the deformations. The matrix structural analysis is what we use in our softwares, or that is a special case of the finite element method. Deflections of structures can occur from various sources, as you have known, due to the dead load, the live load, the earthquake, wind loads, also temperature, fabrication errors, or settlement. In design, deflections must be limited in order to provide integrity and stability of roofs and prevent cracking of attached brittle materials such as concrete, plaster, or glass. So it's important that we know the the maximum allowed deflection for a certain structure. And also, a structure must not vibrate or deflect severely in order to appear safe for its occupants. More important, deflections at specified points in a structure must be determined if one is to analyze statically indeterminate structures. So later on, we will tackle about the indeterminate structures. So you need to master how to compute or how to determine the deflections and rotations of the structure. The deflections to be considered here will be applied only to structures take not having linear elastic material response. It's the analysis for the deflections for nonlinear, that is beyond the elastic limit of the material, is beyond our discussion. The deflections to be considered in our discussion will apply only to structures having linear elastic material response. The nonlinear elastic response is beyond our discussion. So take note that the linear elastic material response is that when you apply a load, come back to its original length, or it will go back to its original length. So if you discuss about beyond the elastic states, then that would be a different topic already. The deflection of a structure is caused by its internal loading, such as the normal force, the shear force, or the bending moment. For beams and frames, however, the greatest deflections are most often caused by the internal bending, whereas internal axial forces cause the deflections of a truss. Before the slope or displacement of a point on a beam or frame is determined, it is often helpful to sketch the deflected shape of the structure when it is loaded in order to partially check the result. So it's very important that you have to develop the skill in sketching the deflected shape of the structure. So anyway, don't worry, we will discuss that here. The deflection diagram represents the elastic curve or the locus of points, which defines the displaced position of the centroid of the cross-section along the members. Take note, the displaced position of the centroid of the cross-section along the members. For most problems, the elastic curve can be sketched without much difficulty. When doing so, however, it is necessary to know the restrictions as to slope or displacement that often occur at a support or connection. So here is the typical effect for the different supports. For supports that resist a force, such as a pin, restrict the displacement, and those that resist moment, such as the fixed wall, will restrict rotation. The deflection of frame members that are fixed connected causes the joint to rotate the connected members by the same amount theta. So as this joint is considered a rigid connection, so whatever is the original angle between them will stay. If it is 90 degrees, and then if it will rotate, then the angle here will be the same as the angle on the other side. In a pin connection, of course, if it is pin connection at this joint, then the members will have different slope here. We have theta 1 and theta 2. Remember, different slope are rotation at the pin, since the pin cannot support the moment. So for these three supports, the roller support, it will create a slope theta, but no bending or no deflection at the support. So with the hands, there will be no deflection, but it's allowed to rotate. So that is why there is an angle theta. Of course, for the fixed support, there will be no rotation nor translation. So the structure should be perpendicular to the support, or the elastic curve is tangent to the support. If the elastic curve seems difficult to establish, then it is suggested that the moment diagram for the beam or frame be drawn first. By our sign convention for moments, a positive moment tends to bend the beam or horizontal member concave upward. That is the first diagram. So if we have the moment here clockwise and counterclockwise, and then the member will be concave upward. That's the effect of the positive moment. Likewise, a negative moment tends to bend the beam or member concave downward. So it will go in that direction, counterclockwise and clockwise. That's a negative moment. So we have a concave downward. Therefore, if the shape of the moment diagram is known, then it will be easy to construct the elastic curve and vice versa. So normally we have to look into the supports, then the moment diagram, then we can finally finish drawing the elastic curve. Here is an example of drawing the elastic curve. We have to consider this beam with associated moment diagram. First, the moment diagram is negative here and then positive on the right hand side. Due to the pin and roller support, the displacement at support A and D must be 0. So you can draw a curve at these two supports, which is with a displacement of 0. But of course, it will rotate. Within the region of negative moment, the elastic curve is concave downward. So this is the boundary between the positive and negative moment. You can just draw a line here, that one. Then the negative moment, the elastic curve is concave downward. But for the positive moment here, and this is the region of the positive moment, then the elastic curve here should be concave upward because it is positive. Of course, if you will see this line between the boundary of the negative and the positive moment, the point at the elastic curve is what we call the point of inflection. This is where the curve changes from concave down to concave up, since this is a point of zero moment. If we have to use the same principle for this beam, note how the elastic curve for the beam was drawn based on its moment diagram. Again, first look at the peak support. This is a peak support, so there will be no displacement, no rotation. So the elastic curve here should be tangent to the structure. And at the other side, there will be movement because there is no support here. It can go down, and this one it can go up, but sometimes it's difficult for us to determine this one, so we need to know the moment diagram. Here we have a positive moment diagram near the support and a negative moment diagram on the right hand portion. And since the moment is positive near the support, then the elastic curve should be concave upward, and also for the negative moment it should be concave downward. And again, at zero moment, the point at the elastic curve is what we call the inflection point. This is the point where the curve changes from the concave upward to concave downward. Also, for the application of deflection curve in RC, this is very important because if you know the elastic curve of the beam, it's very simple to determine the location of the reinforcement to be put in the reinforced concrete. Again, concrete is weak in tension than the compression. So where the tension is, we need to support it with reinforcing steel. So being able to draw the deflection curve also helps engineers in locating the steel needed to reinforce a concrete beam, column, or wall. Concrete is another weak in tension, so regions of a concrete structural member where tensile stresses are developed are reinforced with steel bars called reinforcing rods. These rods prevent or control any cracking that may occur within these regions. Okay, so here is an example, a simply supported beam loaded with uniformly distributed load, and the beam will bend downward, so the elastic curve is concave upward. So the tension is located at the bottom and the top fibers are in compression. Since concrete is weak in tension, so cracks will initiate here, and this is where the reinforcing steel is needed. So with the overhanging beam with the uniformly distributed loading here on the left hand side and a concentrated load at the pre-end. So in this particular case, since this is a fixed support, so the elastic curve here is tangent to the structure, and then as you will know, this is concave upward and then concave downward. So at the concave upward portion, the tension is located at the bottom fibers and the top portion is in compression. So we need to put reinforcement at the bottom. Meanwhile, at the right hand support, the the elastic curve is concave downward. So tension in the fiber is located at the top and compression at the bottom. So the reinforcement should be placed at the top of the secant support. So that is those are the applications of the elastic curve. Here is an example to draw the deflected shape of each of the beam shown. Of course, this is the quantitative drawing of the deflection. It's not quantitative. Quantitative means you need to have the numerical values, but here it's just a drawing, a possible drawing of the effect of the loading. So for uh, different beams, for the first beam, a prop beam, uh, the roller at point A allows pre-rotation with no deflection. So as you can imagine, there will be no deflection here, but there is rotation. But at point B, this is a fixed wall that prevents rotation and deflection. So the elastic curve here is tangent to the structure. Yeah. And since the loading is downward, so possibly the rotation at point A is clockwise. Yeah, and then you have to connect it with point B with concave upward curve. So this is the qualitative sketch of the deflection diagram for this particular beam. For the other beam, a fixed-ended beam with a uniformly distributed loading, since this is symmetrical, then you can just think since you are loading it downward, then the beam will bend downward with the concave upward. And take note, we have two fixed-ended supports, so the elastic curve at point A and point B are tangent to the structure. In the third diagram, this is a beam with a hand support and a roller support, and the only loading is the couple at point A. So of course the beam will tend to rotate clockwise, or the the elastic curve will be concave upward. Of course, at point C to D, this is a straight line because there is no loading at point D, or nor at segment CD. This couple moment will rotate the end point A. Of course, this will cause deflections at both ends of the beam, since no deflection is possible at the supports B and C. Notice that the segment remains undeformed. This is CD, which is still a straight line since no internal load acts within it. For the other beams, sorry, this is not D, but this one. This is the beam D. Of course, there is an internal hinge here. That this will create the same displacement but with different rotations on the left and on the right. And of course, we have the hinge support at A, so this will rotate clockwise. And at point C, we have a roller and the fixed end at point D, where no rotation or deflection will happen at point D. And since the loading is here, so it seems like that the beam will deflect downward. For fifth diagram, this is again a fixed-ended beam with an internal hinge at point B. And since the loading is here, located at this portion, P is applied, so there will be some rotations here. This compound beam will deflect this way. Note that at point C, this is a roller support, so there will be a counterclockwise rotation but no deflection. For the last diagram, this is a continuous beam with hinge support at point A, roller at B, C, and D, with a symmetrical loading of W at the span BC. For this type of beam, it is intuitively shown that the beam will deflect downward, but the adjacent segments CD and BE will deflect in the opposite curve. It is concave downward compared to BC, which is concave upward. Aside from that, we need also to know the qualitative deflection curve for the frames. It's very important that we'll understand. We have four example of frames here. We have in the first frame, just take a look at this frame. At point D, this is fixed support, so there will be no rotation nor deflection at point D. But for point A, this is hinge support, so there will be some rotations but with no displacement. So if you have to apply a force P at point B, then the frame will rotate clockwise, or the columns that are connected should rotate clockwise. But take note that joints B and C are rigid, so there will the angle, which is 90 degrees, will be maintained. The member BC will deform, so that first by the since we have to maintain this 90 degrees angle, this beam BC will rotate. By rotating it, there will be a change in curvature from positive bending to a negative bending. So there will be an inflection point at almost half or at the midspan of BC. And aside from that, in column AB, since this is a hinge support, so there will be a bending in that direction. But at CD, since this is a peak support, so there will be a change in curvature. So there will be an inflection point here. For this particular frame, as you can imagine again, uh, support A and E are both peak support, so the elastic curves will be tangent to the members, but except for support F, which is a roller support, which is free to rotate. So in this particular case, again, this column will have no inflection point except for the outer columns AB and DA, because we need to maintain the rigidity of the joints at B, C, and D. Since initially it's 90 degrees, then it must remain 90 degrees. So if it will remain 90 degrees, then there will be some rotation. So here we have a concave downward, then concave upward. Then for BC, concave upward, then concave downward, concave upward for CD, then concave downward. So with the column DE. So you can see 1, 2, 3, 4 inflection points. And for this particular portal frame with fixed supports at A, H, G, and F, this has a different behavior, especially that the loading is symmetrical. It is only loaded at CD. So first try to imagine that the deflection at A, H, G, and F are all tangent to the column. Again, there will be no rotation or deflection at this portion. So these are vertical lines. And then you can start at member CD. At member CD, since we have a uniformly distributed load, then the curvature should be concave upward. And to maintain the rigidity of the joints, this is 90 degrees, 90 degrees, then the the adjacent spans BC and DE will have concave downward elastic curve. And since again you need to maintain the rigidity of this joint B, it should be 90 degrees. Since this is concave downward, then there will be rotations here also. uh, that is concave upward and concave downward, so that there will be an inflection point here. So with the other side, because this is symmetrical. And of course for CH, column CH, again we have to maintain the rigidity of the joint at point C. So since it has rotated that way, and so that it will maintain the 90 degrees joint, then there will be curvature here in this direction, and then a reverse curve so that it can connect to point X. Again, since this is symmetrical, then these two elastic curves will reflect on the right hand portion. For this particular frame, again with a peak support at A and hand support at F, it is expected that there will be no inflection points here, but at other side at point A, B, and C, there will be some inflection points. So with the beams, so here the force P is applied at point B and point C. So it's normal that the columns will rotate clockwise. But again, you have to maintain the rigidity of the joint B. So there will be rotations here and then the inflection point. And also, since there is no rotation on, or there will be no inflection point at DEF, so the rigid joint here is still 90 degrees, and then it needs to bend downward and bend upward to still follow the rigidity at joint B. So there will be an inflection point here. But the top portion, since this is a hand support, or hence a pin connected joint at joint C. So this joint C, the two members BC and CD will have a different rotation. So it's not necessary that we have to maintain the 90-degree angle here. So this is the effect of this type of joint. Aside from that, I hope you will be able to understand the concepts of the qualitative elastic curve, so that it would be easier for us to check our work, especially if we are working on a software. There's no way of checking the result of the software, but you have to do it manually. So if you can develop your skills in drawing qualitative deflection curve, then you can always check your work. Then now we will discuss the elastic beam theory, which is the fundamental concept used in the calculation of deflections and rotations. Here we will develop two important differential equations that relate the internal moment in a beam to the displacement and slope of its elastic curve. These equations form the basis for the deflection methods, and for this reason, the assumptions and limitations used in their development should be fully understood. So to derive these relationships, we will limit the analysis to the most common case, that is initially a straight beam that is elastically deformed by loads applied perpendicular to the beam's x-axis and lying in the xv plane of symmetry for the beam's cross-sectional area. Here, instead of using the y-axis, we use the v-axis. So it's not really a big deal. You can use whatever notation that we have. We just assume that along the longitudinal axis of the member, it should be x-axis, and the perpendicular axis is v. You can use y if you want. Then, due to the loading, the deformation of the beam is caused by both the internal shear force and the bending moment. If the beam has a length that is much greater than its depth, the greatest deformation will be caused by bending, and therefore we will direct our attention to the effect of bending. There will also be deflections caused by shear, but that will be discussed later. When the internal moment M deforms the element of the beam, then its cross-section remains plane. This is very important in the elastic beam theory. Its cross-section remains plane, and the angle between them becomes theta. So this is the angle if there will be some deformations of the beam. The angle from the horizontal, that is angle uh, theta. So if you have to cut a certain portion of the segment, you follow the rotation. The angle d theta is here with the curvature. The arc dx at the neutral axis that represents a portion of the elastic curve that intersects the neutral axis for its cross section. The radius of curvature for this arc is defined as the distance r. So from O prime to dx. Any arc on the element other than dx is subjected to normal strain. Of course, if this beam will rotate, then the only portion with no strain is at the neutral axis, that is this location dx. There will be strains outside the neutral axis. So, for example, the strain in arc ds, this is before the deformation. We have the arc ds at a distance y from the neutral axis. So, the strain should be equal to this one after the deformation. We have the ds prime minus the original length ds divided by the original length. So that is the strain of this arc ds. However, you have to remember that the ds is equal to dx here before the deformation. Ds is equal to dx, which is equal to the uh, the curvature r, radius of curvature r times rho times dx, or d theta, the angle d theta. So this is dx, rho times d theta. Also, accordingly, ds prime is also equal to the angle rho, or the distance rho minus y times the angle d theta. So if we have to substitute that to the above equation, uh, ds prime is equal to rho minus y d theta, this one, minus ds is rho d theta over ds, which is rho d theta. If you have to redistribute or distribute this term, then rho d theta minus rho d theta will be cancelled. The remaining value should be minus y d theta. Minus y d theta over rho theta will remain minus y over rho, because d theta will be cancelled. So that's why the epsilon here is equal to minus y over rho. Or if you have to interchange this one, 1 over rho is equal to epsilon over y. If the material is homogeneous and behaves in a linear elastic manner, again, our material should be homogeneous and linear elastic. And then the Hooke's law can be applied, that stress is equal to epsilon times E. Or if we have to rearrange the equation, epsilon is equal to sigma over E. And also if we have to apply the Plexure formula, which is stress is equal to my over I, then you can combine these two equations by substituting sigma minus my over I to the first equation. Epsilon is equal to minus my over ei. And also if we have to substitute the values, look for the values here, we have 1 over rho is equal to minus epsilon over y. So by substituting that value, it will result to 1 over rho is equal to m over EI. Take note, rho is the radius of curvature at the specific point on the elastic curve, but the ratio 1 over rho is referred to the curvature, where m is the internal moment in the beam at the point where rho is to be determined, E the modulus of elasticity of the material, and I is the beam's moment of inertia computed about the neutral axis. Remember, the product EI is a flexural rigidity, and this is always a positive term. And since dx is equal to rho d theta from the diagram, this is dx is equal to rho, the radius of the curvature, times the angle d theta. So that's dx is equal to rho d theta, then theta, then we can substitute that into this equation. 1 over rho is equal to m over pi. 1 over rho here is equal to d theta over dx. So by substituting that, we can compute for d theta, which is equal to m over ei dx. So here the equation says that we can compute for the rotation theta according to this equation. Also, if we have to assume that the v-axis is positive upward, and we can express the curvature 1 over rho in terms of the x and v, we can now determine the elastic curve of the beam. But remember, in calculus, the curvature relationship is defined as 1 over rho, which is equal to d square v over dx square over 1 plus dv over dx square to the power 3 over 2. So therefore, the equation is E. Therefore, the equation is a nonlinear second-order differential equation. This, in its solution, v is equal to fx. It gives the exact shape of the elastic curve, assuming, of course, that beam deflections occur only due to bending. So this is quite difficult to solve because this is nonlinear second-order differential equation. But if we have to simplify our computation, the slope of the elastic curve for most of the structure is very small. Take note, very small. So using the small deflection theory and assuming that the slope dv over dx is approximately equal to 0, then as a consequence, its square will be negligible compared to unity. So as you can see in this equation, dv over dx is approximately equal to 0. Then the remaining denominator will be 1. Then the whole right hand side portion of the equation is d square v over dx square. Uh, this is the elastic curve equation of a beam due to bending. D square v over dx square is equal to m over ei. So here, the result implies that the points on the elastic curve will only be displaced vertically and not horizontally. So we can use this equation in our computations of the deflections and the rotations, especially for the double integration method. We are now ready to solve this one using the double integration method. And that would be our next topic. After this, we will discuss that in the next lecture. Thank you.